Before we discuss the algorithms specifically, let's define a few things. The first is a factor. So by factor, we just mean a probability table over some set of random variables. So if I write f of a, b, and c, I could write this down as some table where we have a, b, and c. And for every possible assignment, here we're imagining A, B, and C are binary, but they don't have to be in general. There's some value of f of A, B, and C. And we're not going to require that this factor be normalized. They could be any arbitrary values. We're also, so factors are more or less the same principle as a potential that we defined in the case of a Markov random field. Recall that a potential over some subset of variables is also a probability table, or not necessarily a probability table, a value table over the possible assignments to those variables. And in fact, potential functions are an example of a factor. Another example of a factor would be our standard probability function. If we wanted to write down probability of A, B, and C, we would represent that as a probability table over all the possible assignments to those variables. And in that case, our values would sum to 1. Another example is if we wrote probability of A, B, given C. Note that that expression still gives you a unique value for every possible assignment to A, B, and C. But note that this won't all sum to 1. If you took all the values, if you hold C fixed and look at and all the values of A and B and sum those up, then you'll get something that sums to 1. But the whole table won't necessarily sum to 1. So by factor, we're just generalizing this this property of a table over variables. So we're going to use factors a lot and operations on factors for all of our probabilistic inference. So the reason it's useful to define this as a term is often we're going to write something like f of a, b, or actually let's use the terminology we're going to use in the next section, in the variable elimination section, which is tau of a, b, tau being a specific factor. We're going to write this as, for example, probability of A times probability of B given A. And what we mean here is we're actually, in this expression, we're trying to write down the whole factor tau of A comma B. So if these were binary variables, this would be 4 numbers associated with this factor. And we're writing it as a function of these 2 other factors. So this is more succinct than saying, well, if we, this is a way to compute for any particular value of A and B, we can figure out the values that go into these respective distributions. When we're doing this computationally, and again, we're doing this algorithmically, so we want to see how this would actually be implemented in a computer. In general, when we write down a factor, we're imagining this as an actual table that we would store on a computer. And we would be doing these computations over entire factors. So if there's a line in our algorithm that says something like compute tau of AB by multiplying together these 2 factors, that is to say that we're going to take in 2 probability tables, both of which exist in memory, and output this other probability table. So hopefully that's clear that we're not doing anything mathematically different. This is really just a notational shorthand. And for use when we were to actually implement this in computer code.